So in the last video I left you with the idea that theories of memory were distributed between the localizationist view of memory, that it's stored in specific places in the brain, and the distributed view. What I want to do in this video is to just look a little bit more at some of the formal methods for studying memory that were developed to try and tease apart these ideas, and then I'm going to finish with the discovery that really transformed how we think about memory formation. So I've mentioned Pavlov and his introduction of the associative conditioning paradigm. So this has been an incredibly useful paradigm which we still use today, and it's worth knowing some of the basic principles, because it may be that the associative principles that he developed to look at these very restricted kinds of learning may actually be building blocks of more complex forms of memory as well. So just to introduce you to some of the terminology. So Pavlovian conditioning builds upon a natural behavior, one that already exists. So with Pavlov's own experiment, it was salivation. It could be pupil dilation or sweating, or some type of natural behavior that naturally occurs in response to stimuli in the environment. So we could think of these as hardwired, if you like. And because they haven't had to be learned about, they're called unconditioned. So an unconditioned stimulus like food will elicit an unconditioned response like salivation. So, and then in the Pavlovian conditioning paradigm, a new stimulus comes to be associated with the unconditioned stimulus, so that the animal learns that the new stimulus that formerly didn't really mean anything has come to predict the arrival of some type of meaningful kind of consequence. So the new stimulus then comes to elicit the response directly. So salivation, for example, will start to occur in response to the sound of a bell being rung or a bowl being rattled or whatever, whereas normally it would have occurred only in response to the food. So this is a conditioned stimulus. So the natural stimulus is the unconditioned stimulus because it didn't need to be trained. The natural response is the unconditioned response. The new stimulus is the conditioned stimulus. That's the one that the animal will come to learn about. And then its new response to that conditioned stimulus is the conditioned response. So classical conditioning, or Pavlovian conditioning, uses that terminology a lot, and you'll see in papers that you read, CS and US and UR and CR and so on. They are used frequently. Now, we realized fairly soon after Pavlovian conditioning came along that not all behaviors can be explained in this simple way, because quite a lot of behaviors are not natural. You know, the animal has learned to do things that it wouldn't normally do, like this squirrel, for example, has been trained to do things. And so a new variant of conditioned association began to be studied and formalized, and this is called operant conditioning. So this is when an animal learns that a behavior that it may have initially produced spontaneously or accidentally comes to be associated with some type of reward, and so the behavior becomes more likely. So there was a lot of study of operant conditioning in the early parts of last century. One of the most influential people was Thorndike. So this is Thorndike's puzzle box. So what happens in the puzzle box is that the cat is imprisoned inside it, and then the cat needs to learn to get out, and it eventually discovers if it pushes the door, it can open the door, and then a lever is added, so it has to press the lever and push the door, and so on and so on. And so the task gradually gets more and more complicated, and at each step the animal learns to do more and more things, until by the end it's executing an extraordinarily complex set of actions. So operant conditioning is it differs from Pavlovian conditioning in that it's not built upon spontaneous behaviors, but in other ways it's very similar. We have these conditioned stimuli that come to produce the response. So these are both types of reinforcement learning, and it's called reinforcement learning because the development of the learning is prompted by the occurrence of effects, consequences of the behavior or the consequences of the stimulus that are meaningful for the animal. And reinforcement learning is commonly studied today. So reinforcement makes a behavior more likely, and punishment makes a behavior less likely. So reinforcement reinforces a behavior, punishment reduces a behavior, and both of those things can be positive or negative. So you can have a positive reinforcer, which is something pleasant, or you can have a negative reinforcer, which is the removal of something unpleasant as a consequence of an action, and similarly with punishment. So those are things that sometimes get confused, positive and negative reinforcement. Negative reinforcement is not the same as punishment because it's making a behaviour more likely. Now, some kinds of learning were not easily explained by reinforcement. And one of the very early experiments which really challenged this idea is Tolman's sunburst maze. I'm not going to go into it in too much detail here because we're going to look at it more in some of the videos to come. But Tolman was studying maze learning, and he found that there were some kinds of behaviour on a maze that couldn't be explained by the past occurrence of association with reward, because the animal hadn't experienced those things that seemed to be generating a new behaviour. Now, Lashley's experiments seem to suggest that reinforcement learning might be distributed throughout the brain, but in the 1960s, some new evidence came along that suggested that maybe there were structures in the brain specialised for memory. And the discovery that really revolutionised the study of memory was the case of HM, who I'm sure many or all of you have heard about. We call him HM. Actually, now, since his death, his name has been released. It's Henry Mollison, but we often call him HM from decades of habit. So Henry Mollison was a young man who had temporal lobe epilepsy. So he had a focus of epilepsy on both sides of his brain in the temporal lobe. And at the time, and it's still the case today, if somebody has intractable temporal lobe epilepsy, it can be cured by removing the affected temporal lobe. And so the neurosurgeon William Scoville met this young man who had really debilitating seizures, and he determined that this man had a focus on both sides of the brain, unusually, both temporal lobes. So he said, well, let's remove both temporal lobes. The temporal lobe seems to be a silent area because when we remove it, people suffer no consequences that we've been able to determine. So HM had a bilateral temporal lobectomy. And when he woke up, he was cured of his seizures, indeed, but it was very quickly apparent that he was very profoundly amnesic. So from that moment forward, he was unable to form new memories for things that happened to him. So Scoville and the neuropsychologist that he was working with, Brenda Milner, they quickly wrote up this case together with a handful of other cases that were slightly similar, and said, for one thing, don't do bilateral temporal lobectomies. It's a really bad idea. But also, it may be that in the temporal lobe is a structure that's really central to formation of memory, and they suggested that the structure was the hippocampus because it's the largest structure in the medial temporal lobe. So they suggested that the hippocampus is a memory structure. So this is just to orient you to where the hippocampus is in the brain. So the line diagram is a human brain, but we're going to be mostly looking at rats in this course, and the hippocampus is in yellow. So the inset picture is just to show you why it's called hippocampus. Hippocampus is the Greek word for seahorse, and actually if you dissect out the human hippocampus, you can see that it actually does look remarkably like a seahorse. So that's why we call it that. In the brain of rats and other animals that have less convoluted brains, you'll see that it's much simpler shape and it's more like a cashew nut. So the hippocampus was already known about because it's part of a set of structures in the subcortical regions of the brain called the limbic system. So this is a diagram of the limbic system here. It's a variable set of structures depending on exactly who you talk to, but it includes the hippocampus and things that are feeding into the hippocampus. So, for example, the medial septum in the forebrain, which feeds into the hippocampus via a bundle of fibres called the fornix. The cingulate cortex, which is close to these projections, and the amygdala and the thalamus, and sometimes the hypothalamus is also included. So these structures, they're deep in the brain, and they're also kind of connected together, and as you can see in the kind of wiring diagram, in a kind of a loop or a ring. So limbus is the Latin term for ring. So the limbic system had long been thought of as an emotional system in the brain. Papes and MacLean early on had suggested that the fact that these structures are all connected together is a possible mechanism for sustaining emotions. Emotions tend to last for a long time. You know, if you have an emotional experience, you tend to feel the emotion from that experience for a long time afterwards, and they suggested it was because of reverberating activity around this ring. However, the case of HM suggested that maybe, or additionally, this system may be involved in memory formation instead. Now, study of HM revealed some really important things about memory, and the most important thing was a discovery made by Brenda Milner when she was working with him to try and kind of map the extent of his disability. And she found that there were certain kinds of memory that HM could in fact form. So, for example, the mirror drawing task, which you can see here, is a task that's quite difficult to learn. So you're given a shape in a double outline like the star, and you have to draw a line between the two lines without crossing over the line. So you have to be kind of precise. Now, you can't see your hand with the pencil directly. You can only see a reflection of it in a mirror. So there's a screen between you and the paper, and then you can see a mirror behind it. So you can see your movements reflected. So you're getting feedback, but it's not feedback that you're used to, and it takes a while to get good at this. But then once you've learned it, you can do it quite easily. So HM was able to learn this task, and he learned it at a normal rate, which was very surprising, because clearly this is a type of memory. But he didn't have any recollection of learning the task. So each day he'd sit down and he'd be presented with a task, and he'd say, gosh, this looks like it's going to be really hard. And then he'd do it, and he got quicker and quicker at it. And towards the end, he'd go, wow, this is a lot easier than you would think. So he had really no memory of ever having seen this task before, but somewhere stored in his brain was a memory of how to do this task. So that was the first indication that memory really is not one unitary thing, but it's many different, at least two different things. This is just to show you how he was able to learn the task at a normal rate. So we now know that there are many different kinds of memory. We tend to kind of place them in dichotomies. It's probably not really like that, but it just makes it easier to think about. We've looked at Pavlovian versus operant conditioning. We're going to be looking at response versus place learning, which is the distinction between learning actions and learning places. We're going to learn the distinction between episodic and semantic memory. So episodic memory is memory for events, and semantic memory is memory for knowledge. We're going to look at declarative versus non-declarative memory, which is memory for things that you can consciously recollect and talk about versus things that are more implicit or unconscious, and we're unable to talk about them. We're going to touch briefly on emotional versus contextual memory, and also familiarity versus recollection. So familiarity is, I think I know you, but I'm not sure, versus, yes, I remember when I last saw you. So memory really is, there are multiple different subtypes of memory. And so the question now is to try and understand which bits of the brain are responsible for which types of memory and how do they all interact. So really kind of wrapping that all up, it seems like memory is both distributed and localized to some extent. There are kind of modular subsystems in the brain, but really the whole brain is involved to a greater or lesser extent. So I'm going to leave you with this diagram, which I think is quite useful. It's kind of a taxonomy of memory, showing how it may map onto different subsystems in the brain, and then in later lectures we're going to look at some of these subsystems.